I'd like to welcome you to this first lecture that comes from Chapter 4 of the book Data-Driven Science and Engineering. It's by Brunton and Kutz, and you can find all the details here at databookuw.com. It has all the code we'll talk about today, as well, both in MATLAB, Python, lots of more videos as well for this chapter and other chapters of the book. So the idea today is to talk a little bit about regression, start laying the groundwork for regression, and model selection. This is what this chapter is about. And so regression is this idea of, one way to think about it is curve fitting. And so I want to start introducing that concept, which is typically familiar to most people, and then we'll build it up from there to do more advanced things and think about regression more broadly. So how do we want to think about it? A lot of regression is going to come down to thinking about AX equal to B. And I'm going to show you this from the point of view of least squares fitting, which we typically have done in a lot of our background classes. If you do a line fit to data, for instance, it's a least square regression. So the idea of a regression is to think about fitting a model to some data using some parameters. So you get to pick the model. You have an input set of data and a target, which is the output, and then you fit that model, and you typically have some parameters you have to do this with. And oftentimes it comes down to formulating as an AX equal to B problem. And I'll show that in least square fitting in a moment. But really, more broadly, what we want to think about is that in a lot of these systems, when we do the fitting, we often have over-undetermined systems that we're looking at. So in an overdetermined system, we can't actually satisfy the set of equations. So AX cannot equal to B. So instead, we might do something like set up an architecture. We say AX minus B is minimized, but then out of all the solutions you might want to try to figure out for X, which would minimize this, you might impose a penalty itself on the form of solution. So plus lambda g of X, and g of X is typically called the regularizer. So this regularization process is really critical when we do think about regression, curve fitting, model selection. So this is the overdetermined case, and we're going to come back to talk about these later in these lectures when we start generalizing the concept of regression. But here also we have the idea of underdetermined systems. And in an underdetermined system, you have a lot of variables with very few constraints, which means you have an infinite number of solutions. Well, how do you solve that? You have an infinite number. How do I give you back a solution that might be valuable to you? So instead, what you do is you might say, actually, my objective now then becomes some form of X that I want back. So for instance, I might want an X, or a solution to this, that has the sparsest number of values. In other words, I want most of it to be 0 except for a few terms, or I want a smallest L2 vector coming back. So you get to decide this, and that's your objective function, subject to the fact that you can in fact satisfy AX minus B equal to 0, but oftentimes you relax that to be AX minus B is less than some epsilon. So this is the generic framing of a regression problem in these architectures. I'm going to talk about that in detail as we go along. More broadly, you can think about these systems being nonlinear regressions. So now for the overdetermined case, it's again, I've just replaced AX minus B here by some nonlinear set of constraints. And again, the idea here, if it's overdetermined, I'm going to have to just figure out how to minimize this function subject to something on the regularization, g of X. Or in the underdetermined case, I can certainly satisfy f being 0, but lots of infinite ways to do that. So what I specify is some kind of solution form for g of X. Again, you can make it an L2 type of solution, an L1. There's different options here. And we'll talk about what L2 and L1 mean in a moment in terms of just even standard curve fitting. So this is kind of the generic architecture that you think about with regression. Now the interesting thing about regression is it leads you right away to some interesting issues that can happen. In particular, I'm going to give you two canonical things that you have to start thinking about when doing regression. First is I can make a model. Remember, my objective is to specify a model that takes me from an input to an output, and then specify some parameters in that model. So I could have, in fact, a very large set of parameters to match my input to an output. So you might have a curve like this where the error starts to drop. If I have a lot of parameters to use to make that match happen, my error will drop. In fact, if I use a set of training data, my error might go down all the way to 0. So imagine the following scenario where I have 1 million data points, but I give you a model with millions of parameters. I could use all those parameters to try to make the error go to 0. But the problem with that is what you see here. If I have a set of data that I held out and you try to use that on that data, this is often what will happen. You've overfit the data, and on some new data, you'll get an increased error on that withhold data set. So this is a problematic issue that typically happens when you're in the overfitting scenario. So overfitting is a common thing. We're going to have to think about it. It's going to be a common thing in training neural nets. In any kind of regression architecture, you always worry about overfitting. There's also this issue of underfitting, which is you've gotten a model that, even with model complexity, in an underfitting scenario, you never can drop your error down. Either that's a bad model, or you don't have enough data. And in any case, you just basically put yourself in a scenario where your error, in fact, levels out, and you never actually drop it down to 0 like you do in the overfitting case. So these are the two canonical things that can happen. Generally, more worried about overfitting than we are about underfitting. This is because typically in today's modern data area, we have lots of data, we can produce lots of data. So what we have to be careful about is not to overfit that data. Or overfit use a model to overfit. All right, so let's talk about regression then from a theory point of view. So here's a generic regression framework that we want to use. What we think about here is X are my input variables, Y are my output or target functions. Okay? So for instance, X could be your gene expression, and Y could be an output, which is simply, a label about whether you get a disease or not. So Y can be some abstraction of what X is. Okay? So that's one possibility of what an input and an output might look like. You also could have something in a dynamical system setting where X is the solution at time t, Y, the target, is the solution at time t plus delta t. So it's a very generic format for framing almost any kind of problem where you want to say, I want to give you a model, and I want to fit that model to take me from X, the input, to the output Y. Now what you get to do is specify two things here. The two things are the model itself, F, and second is you get to find these beta values. So the beta represents some vector of parameterizations that you would have available to you for that model that you would optimize over to get you the best fit between the input to the output. So that's the objective. Find the beta values. Okay? I'm going to do a simple example of this in a moment here, which is we're just going to do standard curve fitting. So hopefully everything will make sense in the context of a problem that you should feel fairly comfortable with. So basic curve fitting would do the following. You take some data. Here's the data. So these are a collection of points. There's n of them. And so this is your data. What you want to do now is say, okay, what I'm going to do in this simple example is fit a line through that data. These are x, y points. So here's my model. Y equals f of a beta, where now my model is going to be a line, so it's going to be parameterized by two parameters, beta 1, beta 2. Beta 1 is the slope, beta 2 is the offset. So given some input, mapping it to an output, find the best beta 1 and beta 2 that goes through this point, through these points, okay? In fact, it doesn't have to go exactly through these points because it won't. You only have two parameters and you have n data points to go through. So what you want to do is figure out what are the best beta 1 and beta 2 values. And the way you are going to address that is by actually defining some kind of error metric. So the error metric, and this idea was called goodness of fit. So if I get this model, how well does it fit the data? So here's how we're going to do this. We're going to define a fit as, here's my model, f of xk. When I put in this x of k, I'm supposed to get out y sub k. But of course, my model doesn't quite match the data, so there's some error. What I'd really like to do is minimize this error across my data. Now, there's different ways to do this. In fact, I give you 3 different error metrics here that are commonly used. There's the E-infinity norm, which is you just look at whichever data point is furthest away of all the n data points. You want to minimize that. So just take the difference between what your model tells you and what the data is supposed to be, and make sure you bring that as small as possible for any single point. So an individual point will dominate the error metric. There's the E1 norm, the L1 norm. L1 norm is just looking at the absolute value of the difference between your model and the data point. And of course, there's the least squares norm, which is an L2 norm, which is the square of the differences, square root. Okay, so these are standard norms that you use to measure error. Now, what's interesting is these norms have a big impact on the kind of models you get back. And I'm going to show you that in a minute. And in fact, one of the things that will happen over the course of the lectures for Chapter 4 is you will see that this norm selection makes a big difference in the types of solutions you get back. So I'll tell you that now. How you measure error in the norms you use makes a big difference. Okay? So you want to think carefully about it. I'm going to show you one just simple example here of these different norms in action. What you're seeing here in the top plot and the bottom plot are a set of points. The blue are the data. Now what you're going to see here is I have 3 different norms: the infinity norm, the L1 norm, the L2 norm for the errors. And in fact, I could take those blue data points, and if I use any one of those 3 error metrics and I do this curve fitting, look what I get. They're pretty much almost all the same. So no matter what I choose as a norm, they actually give me very similar results. However, in the second example here, notice what I've done. I've got one data point that's an outlier. So all the blue points are there, and I took this original point and I moved it way up here. So in other words, everything looks like it's on a line except for one point. Now the problem with the L2 norm on this kind of data is it'll take that distance and square it. So it's already bad, so you're squaring that, so it's going to make it even worse. And so when you do an L2 fit for this, look at the line you get here. Actually, here it is, right here. This one here, it lifts it way off. The infinity norm says I'm trying to minimize the difference between any point in my fit, and so look how far off this gets it. Whereas the L1 norm hardly changes. The L1 norm just simply measures the distance, not the square of the distance. So you can see these 3 results are quite different in this computation. And in fact, the L1 norm is often used to do what are called robust statistics. They handle outliers very well, so the L1 norm is often used in those kind of problems where you want to take care of missing or corrupt data. And that will be something that we don't talk so much about right now, except to tell you that your choice of norm has a big impact. So how do we actually compute these variables? So I've showed you the result of this, but now let's talk about how would I actually have a theoretical way of computing how I do this least square regression. And then I want to just show you this little calculation here, and then we'll code this. So least square fitting, remember, was to make the error, the E2 error, be minimal. So really what that means is you have to minimize the sum that was in that E2 error, which is right here, which is the difference between your model, f of xk, minus the true value of what the data is, squared. So if you minimize this sum, that's the solution to the least square problem. So now, remember here, this f of xk is our linear model, which is a line, which is right here. I've replaced it here. So basically, you're going to try to minimize this. Now, whenever someone says you're going to minimize or maximize, you typically think, oh, I'm going to set a derivative to 0. And of course, you might say, well, but setting a derivative to 0 just tells me whether I've minimized or maximized. And so even if you do that here, in particular, when we take this error and I take the derivative of e2 with respect to beta 1, set it to 0, take the derivative of E2 to beta 2, set it to 0. The idea is I've found a minimum. How do I know it's a minimum? Because in fact there is no maximum error. What I can do is take this line and move it as far to infinity away from the data, so there's no maximum error, but there is a minimum error. At least for this example, this is very simple to argue in your head that you're not going to have a maximum error, so a minimum error is going to come out of this. So all you got to do is take the derivative of this thing with respect to beta 1, with respect to beta 2, which gives you some conditions. And those conditions lead you to a 2 by 2 system of equations. Here it is, ax equal to b, where the coefficients of the matrix A are computed right here from the data, from the inputs to the outputs. So you solve this ax equal to b problem to get beta 1 and beta 2, and those are in fact the values of the parameterization of this regression model that gives you the least square error. Okay, so that's it. So this is something you can work out by hand. In fact, any polynomial fit will allow you to work out a similar model. So if you do an nth degree model, you get an n by n system of equations to solve for the parameters of that polynomial fit. Okay, so let's walk through some code actually, because this will help us illustrate what we want to do in this curve fitting procedure. So here's the code we're going to run. We're going to basically make up a model here. So here's how this is going to work. I'm going to do, in fact, some different cases. I'm going to take some data. Here's my XY data. So I give you a set of points. So this is the points I showed you in that graph, actually. I give you, how many points? 10 points. And these points kind of look like a line. So we're going to do just a simple line fit through this. So in this line fit, we're going to go ahead and do that. And we're going to, in fact, do this fit using 3 different norms. The L infinity norm, the L1 norm, the L2 norm. Okay? So we're going to put this in here, and we're going to use, here are the 3 fits, 1, 2, 3. I'm going to use the fmin search command in MATLAB, which is going to do a minimization. And what I'm going to do, I'm going to call these fit 1, 2, 3, which I'll show you what they are in a minute. I guess the initial values of beta 1, beta 2, which are 1 and 1 at this point. I'm not going to send any options in about the numerics, and then I send in the data itself. And what I'm going to get back are new values of beta 1, beta 2 after it's done the optimization. Now what I want to look at is what does a fit 1, fit 2, fit 3 look like, because these are going to be the different norms that we're considering. So here is fit 1. And let me show you what fit 1 evaluates. The error is the maximum of the absolute value of my line fit. x01 times x plus x02. This is the beta 1x plus beta 2 minus y. So that's my line, that's my data, and all I'm going to do is minimize the maximum. So this is the L infinity norm. So I look over all the data and see which of the errors is the biggest, and then I try to, and then it's going to optimize to try to shrink that error down as far as it can from this L infinity norm point of view. Okay, so that's the right-hand side of that model. Fit 2, here it is. Here's fit 2. This is the L1 norm. Here's the L1 norm. It's the sum of the absolute value of the difference. So here's my line fit again, x0 x plus x2. So that's beta 1 x plus beta 2 minus the actual data point, absolute value sum. That's the L1 norm. So I'm going to minimize that L1 error. Okay? And finally, fit 3. Fit 3 is almost the same, except now I take the sum of the absolute value of, here's my line fit minus y squared. Okay? So this thing here is a square of the difference, sum of the squares of the differences. That's your standard least square fitting procedure. In fact, we don't even have to even run it through this code because, in fact, we have an analytic formula, which I just derived previously for this. Okay? So those are what I can do with that. And those are the 3 searches. When I come back out, I use the PolyVal command to now basically take my two numbers for my polyfit. These are now my polyfit. They're the coefficients of the first and the second polynomial, the constant and the linear term. I put this in here, I value them at x of f, which is go from 0, steps to 0.1 to 11, and so I can plot those curves, okay? I can also do this here, again, where what I've done here is now taken this, and I've changed the data, and this is where I added the outlier. I took one of the data points and added the outlier, and I just rerun through the code again. So let's go ahead and run this and see what we get here. So this is going to just reproduce the plot I already showed you, and here it is. All right, so there it is. So this basically produces the three curves. The red dots are in fact the data points. The dotted line, solid line, and thicker solid line, those are my L1, L infinity, and L2 metrics of error. And you can see what I do here for the curve fit. If I don't have any outliers, these three norms almost look equivalent. But as soon as I have this one outlier, which is right there, see this red dot right there, then in fact, look at this, the L infinity norm comes way off the rest of the data. So it's completely biased towards this bad data point. The L1, L2 norm gets pulled off by it as well, whereas the L1 norm kind of sticks with it, barely sees it. So in other words, the L1 is fairly insensitive to outliers in this thing. So notice all we're doing in this regression is just saying, I have a model, I have some parameters of the model. Build me the best model that I've imposed with its parameters that takes me from x values to y values. So that's all the optimization does, and this is what fmin search is finding for you in this case. Okay. So that is the code I wanted to run, and that's it. That's kind of like your basic structure of least square regression that we typically learn in an undergraduate course of curve fitting. But curve fitting is just regression at the end of the day. But your model tends to be, for curve fitting, some polynomial fit to some data. Okay? So remember, regression is just a broader framework where you can specify any model F. It doesn't have to be polynomials. It can be much more abstract than that. And so that's an important piece of this, is that specifying the model and its parameters map the input to output. It's a very generic feature of everything we're going to do in data science in some sense. You can also do more here with the curve fitting, because in some sense I was able to write down analytic formula for the least square case. And you can still do this for other kinds of models where you can, in some cases, linearize data. So I may have some data where I actually would like to do something like an exponential fit here. Not a line, but fit it to some exponentially growing solution. For instance, if you have a population that's growing like this, you don't fit that necessarily to a line. You say there's some exponential growth. Find me the parameters beta 2, beta 1 that characterize that exponential growth. So it's an exponential, not a linear polynomial, so it's more difficult to try to write down some kind of analytic formula for how this optimization works, unless you do the following trick. You can redefine the data. So you can take y, for instance, to be the log, big Y to be the log of little y. So little y is the data I gave you, but now you take the log of the data, you make a transformation from those little x, little y to new big X, big Y. The parameter here, beta 3, is related to the line fit log beta 2. So beta 1 now becomes, in fact, the same beta 1 for the line fit. So this turns into a line fit in this new coordinate system, and then you can use the standard formula we have here. So really what this involves is this transformation from the original data to a new set of data, which is taking the log of the y values, doing a line fit now on that data. And if you do the line fit on that data, it's very simple to do, and then you can retransform back. So it doesn't just have to be polynomials. There are certain functions that allow you a way to linearize the data so that you can still do these closed form analytic solutions for fitting. So that's a basic shell of a warm-up that you might think about for regression, curve fitting. Curve fitting is something few people feel fairly comfortable with, have a good understanding, intuition about how it should work. I've shown you how you can derive these results. But more interestingly is the fact that curve fitting just simply sits underneath the umbrella of regression, which is I can give you any model f that maps some value from inputs x to an output y with some parameters beta of that model. And my goal is, given that f, find the betas that give me the best match between x and y, and also understand that the norm you choose, when I say best fit, the norm you choose to measure that best fit really matters in terms of the kind of results you're going to get out. And we'll talk about some of this as we go through this chapter. Again, everything can be found here, databook, uw.com. You can find all the code, both the Python and MATLAB code, as well as the notes. There it is, databook PDF off that website. And if you download that, you can basically have everything you need to explore this on your own, on your own computer.